Hello everyone. In this video, we're going to do a quick walkthrough through Quartus, how to create a new project, how to make a simple design, how to simulate that design, and then we're also going to annotate this. So this will be a good example of the kind of annotations you want to make in your simulations when you submit lab docs. So I'll go ahead and share my screen and we can get started. So right here, you should see Quartus, and this will be the home page whenever you open up the application. So we're going to create a new file or a new project by either clicking New Project Wizard or going up to File, New Project Wizard. So first, it's going to ask for the working directory of this project. In my case, I'll keep them here under Desktop. Let's see, Quartus projects. 3701, and we'll do it here, course tutorial. So an important thing to note is for your directory, you really want to try as hard as you can to save them on your local machine. So here, when I took the class, I didn't realize, but my desktop was in OneDrive. So if you have these projects on the cloud, they could cause issues with opening them sometimes. So you want to avoid that as much as you can. So we'll go ahead and name this project Quartus tutorial. Make sure to use like no special characters, as that will cause some issues with the file path. So we're going to click next. We'll have an empty project, no files to add. We'll go board. We're using the Max 10 DE10 Lite, and we will make sure to uncheck this top level design because we don't want Quartus to create it. We can do it ourselves. So we'll go ahead and click next. Our simulation tool will be Model Sim, and the format will be VHDL. So it'll click next. It'll give us a little summary. We can make sure everything is correct. Our directory, family name, board, model sim VHDL, and then we can go and click finish. So now Quartus is going to generate our project with all of these specifications, and we'll be able to start on our design. So if you notice here, when I try to click on Quartus tutorial, it says can't find design entity. This is because we unclicked that box earlier. So we'll go and create our own. So here you can click new block diagram or schematic file, or you can also click new and then go here to block diagram. So it'll open up our block diagram. And whenever you make a new BDF or block diagram file, you're going to want to give it a meaningful name and description. So here I'm going to say Quartus tutorial video, click enter. My name, which is Landon Amaba, my class number, 11598, which is what it was when I took the class. We'll say our pie's name. I'll say Landon. And then we're also going to want a description of like what this design does. So here, since we'll go ahead and make a half adder in this video, so I'll say half adder. Since a half adder is a very common component, you can leave it there. But as you get to some more complex designs, it wouldn't hurt to add a little more description. So if you think about how binary addition works, if you add 0 and 0, you'll get 0. If you add 0 and 1, you'll get 1. And I can go ahead and also write this out so it's a little more clear. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And then 1 plus 1 is the tricky one. Normally, if you're in base 10, it would be 2. But since we're in binary, the binary representation of 2 is actually 1, 0. But since we can only use one place, um, we'll have to add another signal for the second one. So if you just look at the first, you look 0, 1, 1, 0, based off this counting order, like, wow, that looks familiar. It's going to be our exclusive OR gate, where it's only true if either one is true, but not both. And then we'll make a second signal to handle this 1, which is going to be like our carry into the next place. So we'll start by adding a gate by either clicking this gate icon, or we can double click here in this window, will pop up. And so there's a whole bunch of libraries. but it gets really confusing and difficult to find the gate you're looking for. So we'll use this box right here called name. So I'll type in XOR, which is exclusive OR, and you'll see it pops up. But let's say I wanted an AND gate. Notice how AND doesn't pop up and OR doesn't pop up? This is because we need to specify the input signals, like how many there are. So now if I click AND2, here's our AND2. If I want a 4-input AND gate, I say AND4. And this will work at any primitive gate. So let's say I want a board 2. A board 2 will pop up. So we'll go ahead and get our XOR gate right here, and we'll add it to our design. You can use this zoom in feature right here by clicking the magnifying glass. And first we'll go ahead and add signals. So we'll drag it out from the gate. So these are all wires that will be going in and out. And let's say we name them A, B, and Z. So with this naming convention, they're all assumed to be active high. But if I wanted A to be active low, for example, this is how you would label it. But for the purpose of this video, we'll have all active high inputs and outputs. So the next step is we'll actually need to define these inputs and outputs. So we'll type an input here, and an input will pop up. So actually, we'll do an output first, since we just have one for now. So we'll have our output. We'll change the pin name to Z. And you notice after I clicked it, it disappeared, and I'd have to go back and add another. If we add our inputs, we can actually click this repeat insert mode. I can add an input, and now it prompts me so I can place a second, a third, a fourth, and however many I want until I click escape. So since we only need 2, we'll settle for these 2. We'll call them A and B. And notice how they match up, this A, this A, this B, this B. So it's essentially saying that this input is directly tied right here. But we do this through labeling. And this is case sensitive, so make sure you pay attention to that. So now we have our inputs and outputs defined. We have our exclusive OR gate. So this will handle the first 3 operations, 0, 0, 0, 1, and 1, 0. But then how do we specify that there's going to be a carry here? So in all these other examples, this is like really 0, 0. This is really like 0, 1. This is really 0, 1. And so we can kind of look at the pattern and notice that every other second place right here will be a 0, except for this one. So that's another familiar truth table, which is our AND gate. So we'll go ahead and add an AND2 to input AND gate. There's 2 ways to do this. We can first drag the input up to A and connect them physically. Connect this one here. And this will take the inputs and power this gate. Or the more cleaner, more effective way to do it is create these wires and just give them the same name. So these 2 methods are effectively the same thing. And now we'll have an output. We'll call this cout or like carry out. And remember, we'll have to add another output. So we'll add the output right here and give it the same name. Cout. All right, so now we have completed our design. And now that we've done a design, we think it'll work. We always simulate before implementing on hardware. So let's go ahead and save, Control S, save it right here. And we'll need to run an analysis and synthesis so that it'll be able to take these blocks and convert it into something a computer can read and simulate. So if you notice, there's these 3 arrows right here. For just simulating, we can get away with just running analysis and synthesis. But if we actually want to push this design onto our DE10 Lite and hardware, we'll have to use this arrow without the green check. This is our full compilation. It'll do everything including analysis and synthesis. It'll lint our design and it'll create the netlist and everything. So we'll go ahead and do analysis and synthesis. Down here in the bottom right, you can see 4%. Total elapsed time is 8 seconds. So this is a relatively small design. Oh, so it looks like we got an error. So let's see what this error is. This logic function of type and2 is already defined as a signal name or another logic function. So this is a common error you might get, especially if you copy gates. So I'm glad this happened. So when it says instance, notice at the bottom of each gate, it says instance, instance. These need to be unique to each gate. So like for this one, maybe we'll change it to instant 1. And this one, we'll change it to instant 2. So this will now differentiate the gates when it runs its synthesis. So we'll go ahead and save that design, try to give it another run and see if it'll compile this time. So that is a very common error you'll get, especially if you copy and paste large blocks of code. So now it looks, we got to 100%. It'll pop up with this compilation report, and that means our design will work, or it'll compile. So now we'll actually open our simulation by doing new, and we'll do University Program VWF. And it'll pop up with this nice UI. The first step whenever you have this is to clean up the way it's kind of laid out. You start a grid size. I do 10 to 25. So it'll space these out a little more. And then set end time to 1.2. So if it's 1 or under, sometimes there's issues with the simulation. So 1.2 is a good spot to set it to. So now we want to add our inputs and outputs. So all you have to do is double click in this white space, say insert node and bus. We'll say node finder, list. And these are all the inputs and outputs that we defined in our previous design right here. Or in our other thing where we create the inputs and outputs. So you can select one and click over just to select one, or you can do these double arrows and it'll pull over every signal. So we'll click OK and OK. And now this left side is populated with our inputs and outputs. So notice how there's like X's here on the outputs. This is because we haven't run the simulation, and these outputs are basically undefined. So since we want to count our inputs, we're going to need to group them. You can do this by selecting your inputs, right-clicking. Under grouping, you can click group, and we'll call this like IN for inputs. And now the signals kind of group up, and it's an easy to read binary format. And since we want to count it, we'll select this group. We'll go up here to the C value, click count, start value at 0, increment by 1. And let's say we want to count every 50 nanoseconds. So we'll start that. And now you can see it counts from 0, 0, all the way up to 1, 1, and then it'll repeat itself onward. So now it looks like we're ready to go ahead and save, Control S, and then actually run a functional simulation, which you can go by clicking this or clicking simulation, run functional simulation. So it'll generate the test bench, the netlist, and it'll actually run it. So now we have the outputs based on our inputs. So let's take a look to see if this makes sense. So if you had 0, 0, you'll have a 0 with no carry, 0, 1, and 1, 0. We'll both have a 1 with no carry, and 1, 1 will produce our 0 in the 0th place, and a 1 in the 1th place. So it looks like it's correct. It repeats itself consistently. So it makes sense to us. So now let's make annotations so it'll make sense to anyone else that might want to double check our design, or confirm that what we have is actually correct. So if you're running Windows, you can say Windows Shift S will pop up a little snipping tool. So I'll go ahead and snip, and we'll say 3 of these patterns. So this is 600 nanoseconds. It'll copy it to your clipboard. I'm going to go into OneNote, which is my preferred way to annotate. or other term. Annotation. There's some things you want to consider. The first one would be repeating patterns that you can point out. So for this one, you can notice that there's kind of a pattern right here to the one, and then the same pattern is right here after the second one. So you can indicate that this is the pattern by knowing this like pattern one, or instance one, instance two, instance three, it repeats. And then the kind of really clear, outputs will be the same. So now let's take a look at the actual pattern itself. I'm 0, 0 to 1. Then try to change my pen color. And let's say we want to just deal with this portion over here at 0, 0. We can say something that takes these zeros and makes it into something we can insert. Like 0 plus 0 equals 0. Then this one makes sense why this is low. Maybe a point 0, 1. Switch colors. 0 plus 1 equals 1. So this explains why this goes higher. We can do something similar here. 1 plus 0. And then since this one section is kind of taking a minute to update here on my laptop. This one section, this is kind of what we consider to be the most important section in the simulation, since it doesn't really make sense if you understand how an application works. Now, it's an important thing to do heavy annotations on is the point. So you can say like 1 plus 1 equals 1, 0, and then the 1 is at the key, and the 0 is on the output. So these annotations will refresh soon, and then you'll be able to see everything I've written here. OneNote can be glitchy sometimes. If not, just put a picture of it at the end of the video. So I'm going to annotate. I'm going to annotate this first bit, which we've already said repeats here and here. These are the type of complex designs will become even more important because it's very easy to understand what's going on. Let's say 10 minutes, 15 minutes. You focus on what's important to you as a designer, especially if you're looking for a certain application, like an industry, the industry is going to be checking your design. It's about time understanding it. So, let's see, the petition still hasn't shown up yet. So, we can just attach a screenshot to the end of the video so we'll be able to see what a complete annotation will look like. So let's get moving for this video. That was a quick tutorial of how Quartus works and the annotations you'll make.